All right, one short video in sort of this learning unit. Um, we're going to talk about the Cori and Cahill cycles. So I'm drawing little boxes right here because I'm going to highlight these are the boxes from this slide. If you haven't watched this video yet, okay, what we're doing is we're talking about down here. I'm going to give you a little overview first and we'll summarize it sort of on this slide. The Cori and the Cahill cycles basically connect skeletal muscle and liver, and specifically connect the waste product of pyruvate to sort of a separation in time and space of handling this product of anaerobic sort of fuel metabolism. So when we've got excess pyruvate, there's two ways that you can deal with it. You can convert it into lactate or to alanine. You use transporters that allow you to export it to the bloodstream from the skeletal muscle. It gets uptaken by the liver. The liver is fundamentally going to reconvert it into pyruvate and then can reconvert it into glucose. So that's sort of the net of what's happening. We talked about within this slide, but we're going to just sort of zoom in and look at it here and just kind of isolate it to these two tissues. Now, here's again why this happens. And the Cori and the Cahill cycles are different because of what they do with this excess pyruvate. So remember, when I have slides like this, the left and the right side will sort of talk about two different things, and anything that we put in the middle is things that are common. So what's common is that we have excess pyruvate. So again, why would you have excess pyruvate? You are likely doing a lot of glycolysis, a lot of anaerobic glycolysis. Remember, that's a rapid but inefficient way to make ATP. And so you have this accumulation, but the problem is that you are going to be able to feed back and inhibit glycolysis. So excess pyruvate feeds back and inhibits glycolysis. And again, if you've done a lot of glycolysis, you're generating a lot of NADH, you're deficient in NAD+, so you sort of need to regenerate that NAD+. So as we're going to see here, the conversion to lactate actually is a twofer, if you will. We're going to do both of those, whereas conversion to alanine only helps sort of with one piece. So to put that down sort of in words is what we've been saying. Why might you have excess pyruvate? Is you're doing a lot of anaerobic glycolysis. And the problem with anaerobic glycolysis is you are going to be generating high concentrations of NADH, right? You need NAD+ to do more glycolysis, and you're having excess levels of pyruvate. Okay? Both of these are going to feed back and inhibit more glycolysis. So if you have some way of getting rid of that pyruvate, you have some way of regenerating NAD+, that's going to help all the way around. So let's talk first about sort of the Cori cycle. I want you to remember that the Cori cycle deals with the accumulation of excess pyruvate by converting it into lactate. Okay, the enzyme for that is lactate dehydrogenase. And importantly, one of the metabolites that it regenerates is NAD+. So because pyruvate is reduced to lactate, something needs to get oxidized. And what gets oxidized is NADH to NAD+. So we've got sort of that twofer. We not only deal with elimination of pyruvate, and so we're going to be able to then continue glycolysis because that inhibitory feedback inhibition is not happening, okay? But we regenerate NAD+. So what's going to happen now, and we'll look at this in the picture in a second, we're going to export this to the liver. Okay, then we're going to have lactate dehydrogenase that's in the liver regenerated into pyruvate. And then we can make it back into glucose in the liver. And you'll notice I've come back to the center point of my slide here because we're going to then see a common theme for what happens in the Cahill cycle is we are going to regenerate glucose that can then sort of help with what's going on. So let's just zoom in and see if we see sort of those pieces happening with our picture here. All right, so when we've got glucose that sort of comes in and we are undergoing glycolysis, the purpose of generating ATP rapidly, although inefficiently, let's see if this color shows up okay here. Maybe we'll do this one. So again, this is going to be rapid, but inefficient when we are doing anaerobic glycolysis. So what we do is we do sort of that 11th step of glycolysis, right? After we complete and generate pyruvate, we're going to then generate lactate. Lactate gets exported to the bloodstream. Athletes know this, right? You have lactate accumulation in your muscles after extensive physical work. So sometimes they'll tell you, hey, elevate your legs. That helps actually drain, if you will, that lactate from your muscles and allow it to go to your liver. So lactate's going to get exported, taken up by the liver. We're going to have not only reconversion into pyruvate by lactate dehydrogenase chemistry, but then gluconeogenesis is going to regenerate glucose, get exported back out to the bloodstream to allow it to be reused, right? So a key here is that we are doing a separation in time and space. So we're going to separate in time and space. So the space piece has to do with the fact that we are taking these metabolites onto the liver. We're doing it in a completely separate organ, right? Of course, the muscles can't do gluconeogenesis anyways, but this time piece is we cannot live in an anaerobic sort of environment long term. At some point, that oxygen debt has to get paid, and that oxygen debt is just getting paid later, and it's getting paid in the liver. So we're going to pay this oxygen debt later. Okay? The last piece here is a little bit simpler to think about in terms of the biochemistry of the Cahill cycle. We actually talked about the Cahill cycle when we did our glycogen metabolism case study, right? When we talked about glycogen storage diseases, and we talked about poor Alex, and he was supposed to be exporting alanine to the bloodstream, right? That's what happens normally. And so again, now we're going to see why that happens normally. If you've got excess pyruvate, you can have alanine transaminase. Remember, we talked about those transaminase chemistries are going to interconvert alpha keto acids and their cognate amino acids. So the pairing is pyruvate and alanine. So alanine, again, is going to be exported to the liver. And just like we see over on the left-hand side here, we are going to have a liver isoform of alanine transaminase, and that's going to reconvert it into pyruvate in the liver, and then gluconeogenesis is going to reconvert it into glucose. So let's actually talk about that process. This is gluconeogenesis is going to allow us to reconvert pyruvate, now contained within the liver, back into glucose. So let's just look at the picture for that, and then that'll be it for this short video. All right, so again, if we've got an accumulation of excess pyruvate, again, this process is anaerobic glycolysis. Transamination chemistry, again, it's going to be alanine transaminase because that's the interconversion we're doing is between pyruvate and alanine. We're going to have alanine then that we can export to the bloodstream. Remember, that's what we talked about in our glycogen storage disease case study. Normal anaerobic sort of fuel metabolism in muscles is going to export alanine. Alanine gets exported, liver is going to take it up. We're going to reconvert it into pyruvate by a liver isoform of that ALT, that alanine transaminase. Gluconeogenesis reconverts it into glucose, and then we've got glucose that we can put back out into the bloodstream. So nice little short video there, sort of taking and kind of expanding on the chemistry that happens between the Cori and the Cahill cycles. One last thing to map on. Oh, we should know this. If we are, let's do that. We're going to just zoom in here and highlight. You should be able to label the transporters that we have here. So this is going to be GLUT2 that's exporting glucose from the liver, and then this is going to be GLUT4 that is importing glucose into skeletal muscle. Sort of same over here, right? The glucose transporter that we have on liver is GLUT2, on muscle is GLUT4. All right, now I think I said everything that I want to about the Cori and the Cahill cycles.